Reading. The last video we talked about the gauge instrument of the Moscap. So for today, we are going to talk about the more details of the Moscap, how it works, and for the lastly, the Mosfet. So let's go first. Accumulation. In these sessions, the major let's see, this Moscap is constructed as a metal or N-type heavy doped polysilicon. And for the middle, oxide side. And for bulk or body, we call this as a P-type doped silicon. So for the accumulation situations, we can see that the parent state is nearly the energy balance state or level. And when the parent level is getting more closer and closer to the surface, which means between the oxide and the P-type doped silicons, we can see that the time difference between the bulk and the surface is very different. So what it means, in the bulk, the concentration of the hole is more or less than the surface hole concentrations. So surface hole concentration will be bigger than the bulk hole concentrations. So what it means, see, here the minus voltage biased, and here the positive voltage is induced. So when the P-type of silicons and get the positive voltage, then the holes will be refused from this voltage and they will gather or attracted by the minus voltage from the gate. So they want to go to the metal side, but since there is oxide, they will be blocked. So they can get the metal or N-type polysilicon. And they will use well, last time we I'm going to test for more details. Metal voltage can be used. So difference between the metal and the silicon energy is rather different. Like this. And third, depleted and immersion with immersions. Let's see. In the gate, positive voltage is induced, and in the silicon or solid surface, minus voltage is induced. So what happens? Here we'll make some depletion. When you see the surface energy parent state, there is less or no carrier in the surface between the oxide and silicon. So here we make the depletion layer region. And one more thing on is electrons will start to gather here, but very slowly. And fourth, strong inversion. This will happen when the gate voltage is same or over the threshold voltage. When the gate voltage bias is over the threshold voltage, the electrons start to gather, and when you see here the graph, so with the energy band diagram, the parent state is at the bulks. So I will paint for more details. The difference between the parent state and energy of balance state difference is same at the surface between the energy of conduction band and parent state. So we know about this equation, but gate voltage equals to platinum voltage, adding the voltage of oxide and the surface potentials. So I say strong inversion happens when the gate voltage is same or more than the threshold voltage. So at this station, the equation will change like this. more fun thing is I see here's difference and here's the distance or difference will be same. So let's see if we draw an intrinsic of the pattern state, we call this difference as theta b, and also it will be same here for theta b. And look at the surface. The surface pressure is here and also in here. And as you can see, surface pressure will be same as the double of the theta b. So this will be happen when the pattern state and the intrinsic pattern state difference is double at the surface tension. So we call this a strong inversion. And at this state, the minor carrier for the p-type of silicons, electrons will get at surface. Similar to the accumulation, but they cannot pass to the metal. So they will gather and gather. And when you see at the surface, electrons concentration is very high. As it was one of the silicon that doped as n-type. So this is totally the p-type silicons. And take this to the capacitance. We can see this. The acceleration, the capacitance, total capacitance will be same as the oxide capacitance. And in depletion, the charge of gather will down and reduced. So we can draw this, the reducing capacitance. And for first, weak inversions. For weak inversion, electrons to start gather, but they are weaker than the strong inversion. So they will, when the voltage of the gate gradually rise, the electrons will start gather more, and they will make some capacitance more. We know that Q equals to C, capacitance and voltage. And for lastly, in the strong inversions, the capacitor capacitance will be equal to oxide capacitance. So look here, the depletions, for the accumulations, there will be a capacitance of the oxide. And for depletions, there will be two capacitance, oxide and depletion capacitance. So we learned that if there is two capacitors or lots of capacitors in series, like this, total capacitance will be reduced. So equation will be like this. Okay, thank you. This is the last of the Moscap. And we will go to next the Mosfet. Okay, the second topic will be the Mosfet. Mosfet means metal oxide silicon and field effect transistor. I just wrote here. And let's see with the size of the n-type Mosfet. So n Mosfet means that induced channel will be the n-type, which means electrons are gathered and making some bridge like between the ground and ground. So through this channel and channel, there is a lot of electrons flow, and when let's guess, we have induced sufficient voltage that the gate voltage is over the threshold voltage. By this condition, we can make the n-channel induced between the source and drain. So, and for second conditions, let's guess, at drain we induce positive voltage and source grounded. Then, let's see, electrons will be attracted to the positive voltage, so they will move to the from source to drain. This is why we call this sector as source, since the electrons came up from this side and they will go to here and drain. They will suck off all of the electrons that came from the channel. and this will make the current with the opposite of about the electrons move. So we call the current induced as IDS from drain to source current. So let's clear about the equation of IDS. Let's guess we take a small tiny block from the channel. Set the width as constant, and the length of this surface will be about y axis and x axis. 3 dimensions, but I just thought the z axis will be constant, the width, so just see only 2 secondary dimensions, x axis and y axis. So by multiplying this surface and the width will make the total charge of this block. So I wrote the equations here, but if I talk about this more detailedly, then it will take long time. So I'm gonna skip. I believe you all guys know about these sectors. So if we acquire the equation about the current about the from drain to source, IDS will be length of the gate and the width of the block or pet, and multiplying the capacitance of oxide here, likely the Moscap, and mobility of carrier. Since this is about the MPET, the engineering is Mosfet, I will talk about the electrons mobility in the electric field. And ground voltage, subtracting insulation voltage, and then multiplying the voltage from drain to source, and inducing the drain and grounded to source. And separating about the double of VDS, I dividing half. So this is the normal equation of current about the from drain to source. So let's guess if the voltage from drain to source is tiny and very small to sufficiently small to ignore, then we can use equation as a linear equations. And this is 0. Okay, and more on conditions. If the voltage separating the threshold voltage is over the voltage that induced in the drain and source, they will keep this channel as connected from source to drain, but in one conditions, that is voltage of gate separating the threshold voltage is smaller or same than from drain to source voltage, the channel will pinch out. So here will be pinch out. Pinch up means the channel is somewhat cotton. So by distance from source to drain we move. The channel will be narrow and narrower, and it will make some saturations. Saturation will be talked about later. So at this situation at pinch off state, we accurate the equation of the current from drain to source like this. So here, when the VDF is equal to gate voltage and the threshold voltage, we inject this to the VDF and it will make it like this. At these equations, when injecting the VDS or the gate separating the threshold voltage, equation will be like this. Okay, for the second step, we will look about the second dimension of the N-type Mosfet. Let's start first with the energy state energy level, as we have been tried. So see about the heavily doped N-type silicon. Will be close to the conduction band and far from the valence band. And for the substrate, we know the substrate will be P-type silicons. Okay, so opposite side will be symmetrically same. Those things draw here. Okay, in this condition, we guess any voltage source is not induced in the gate or drain or source or body. So first, let's guess we induce the voltage in the gate. So positive voltage, then the gated enrichment diagram will be down. The more strongly we induce the voltage positive, then the state will be down more and down. So it means that heavy N-type of silicon, there will be a rush of electrons by the density state and less almostly none of the hole. And here, few electrons carrier and rush of hole carriers. And here symmetrically with the entire heavy doped silicons. Okay, so we induce the voltage in the gate positive. It means the barrier voltage will be downscaled, so it means there will be more probability that electrons will be here. Of course, the percentage of hole will be there, probability will downscale like this. And for a second, we induce, let's get the right side will be drained and left side left source. If we induce the voltage in the drain, then the set will be down like this with a weak voltage, and when it came with the more strong voltage of the positive, it will be down like this. So more electrons will be here. Okay. So it means as the energy band diagram state is getting down and down when it goes to the right side, I mean drain side, then electrons will be more each to pass through the depletion region or channel, and they will be pass easily from this energy band diagram. Like this, the slope is negative, so electrons will move easily more to drain. Left side is source, gate, and gate directly, and drained.
Yeah.
And now we know that the current about from drain to source will be like this. And guess this is a linear equation if the predicate is too small to ignore. And this equation will be about the linear state equations, and the slope will be determined by voltage from drain to source. So during the graph about the current from drain to source and voltage about gate. Here is the threshold voltage when the voltage gate passes the threshold voltage, then the the current will be increased linearly by these equations. So if the voltage from drain to source is more larger and larger, the slope will be more steep, and if it was smaller, then it will be more downscaled. Like this, okay. So, one more point. We talked that, subtracting the voltage gate from the threshold voltage is smaller than voltage bias in the drain source. It will make the pinch off situations. So, here is one more graph. Oh, sorry, not voltage from drain source, the gate. So see, about this situation, the equation will be moved like this. So, in the saturation current, here will be the saturation current. And here will be the toroidal regions. So why saturation current happens? See, there is source here and drain side here. If the drain voltage is stronger than subtracting the gated voltage from the threshold voltage, then channel will be more narrower and narrower as the voltage from drain is increased. Then finally, at some moment, when the voltage of drain from drain to source is same as the gate voltage subtracting the threshold voltage, it will make the pinch off situation as I said previously. So, the electron current will be limited. So more detail. Here is the cut-off channel. Here will be the depletion region. So we know in depletion regions there is very strong electron field. So electron gets at the end of channel they cut off, and by the electric field, electron will move to the drain by the electric field power, and it will make the current flow. But we know since the channel is narrowed and keeps its shape, the current will be same. So we call this region as saturation current. And for triode, we can say like this. The channel is not cut off yet, but it's getting narrower and narrower. But since the more voltage at the drain is induced, the electrons will move more faster by these voltage attractions. Okay, this is how the relationship between the IDS and VDS. And one more point, we will talk about the operation mode of the Mosfet. First, for the N-type FET. The patch we talked previously is about the N-channel type Mosfet enhancement mode. It means if you don't induce the gate voltage that overcame the threshold voltage, it will make channel or not, it will not make any channel induced. So if the gate voltage is smaller than threshold voltage, though you induce the voltage in the drain, there will be no current flow. There will be no current flow since there is no channel induced. But if you induce the voltage, gate voltage over the threshold voltage, it will make the channel here and it will make the current flow. And for that, so IDF and gate voltage equation or relationship graph will be like this. And for second, we do know any voltage induced in the gate. There is n-channel induced. So it means the threshold voltage in the negative. So there is only channel induced already. So just inducing the voltage in the drain source, it will make the current flow. Same for the p-type. Just think. P-type what will be made the from drain source. Induce the negative voltage for the same condition of voltage of the gate. When the voltage gate is smaller than threshold voltage, so IDF and voltage gauge equation or graph or relationship will be like this. And for the so we call this the P-channel Mosfet enhanced mode and the last. Separation mode. I forgot about saying that without any gate voltage induced, we call the mode as depletion mode since without any voltage gate, the channel is already induced. So in depletion mode, without any voltage, channel is already induced here. So it will be about P-type channel. And when the core moves to the drain, the current will be moved to the same current, same directions. Without any voltage gate induced. Okay, thank you. And we will go to the last step. Okay, final step, we are going to see about the capacitance of the N-type Mosfet. So first, we are going to see about capacitance between the gate and the channels. So between the gate and channel, there will be first outside of the for first, we are looking for the inversion situation. In inversion state, we can see the outside capacitance and capacitance of depletion and the junctions that induced by the source and drains from the source and drain to piece of space by the region of the depletion here. But look here, the surface is grounded, so we will ignore about the capacitance of depletion. So in inversions, the total capacitance will be over C of the outside and diode junction capacitance between the source and drain to piece of it. And for second, the depletions. In depletions, depletion region will be larger and larger. It means the outside scale will be down. By the depletion of the capacitance will be upscaled. Like this. So in the serial, the capacitance are being, then total capacitance will be down. So it means when the depletion of capacitance is upscaled, then the capacitance outside will be downscaled. So in the depletion mode, capacitance of outside will be downscaled, but as the depletion ratio will be larger, the junction capacitance between from the first drain to piece of plate will be larger. And finally, accumulation. In accumulation state, the depletion ratio will be very small. only between the from source drain to P substrate or the accumulation of holes here. So the junction node capacitance will be nearly small, so it will be likely to zero. So drawing the graph about this capacitance of gate and channel, it will be like this. Inversion, inversion. Sorry. In accumulation, it will be about nearly zero, and depletion, it will be gradually up, and in inversion, value will be likely to capacitance of either side. And second, the capacitance of between the gate and body. So let's start with accumulation state. In accumulation state, we can see in accumulation state, holes depletion region will be very small, and there will be holes inside the body. So what we can see is the oxide capacitance here. Okay, so for the accumulation, there will be only oxide. Of course, there will be other capacitance like fringing or anything else. But since they are very small, for this time we are just looking for the big ones. So for in the accumulation state, there will be only capacitance of oxide. And second step for the depletion mode. For the depletion situations. In these situations, the depletion region will be induced. There will be capacitance induced from the source drain to body, and then the capacitance oxide and depletion region's capacitance. Here we ignore about the capacitance of P-N junctions between the source drain to body substrate. Look here, heavily doped and silicon is grounded. And for last, inversion mode. In inverted state, there will be a channel induced by the electrons. So, the oxide will be nearly gradually down and will be zero. And also, depletion will be also downgraded nearly to zero. So, in inversion, for the ideal situation, it will be zero. So, drawing the graph, we will write this. Accumulation, depletion, and inversion. So, by integrating the capacitance from the gate to the channel and the capacitance from the gate to the body, we will total capacitance of the Mosfet. So integrating these two graphs, we will work like this. Okay, thank you for listening, and this is the end of my short video review. Thank you.